All right, let's do an internal forces example. This is for a frame that we had looked at in the previous lessons, and there was a two force member over here that was CD. Here I'm just saying that this is the force from CD. So this, we're kind of extending this example that we've already solved a little bit further so that we can find some internal forces. And I said, let's find the internal forces just to the right of point D. So here's point D, and I'm saying just to the right. I can't cut at D because there's a concentrated load there. So I'm saying just to the right of it. So one other thing, if you're going back and comparing notes, is I went ahead and showed more significant digits in these answers than there were in the original example. If you recall, the original example was looking for solving for the reactions RAX and RAY. And so I left them at 3 significant figures in that example. But to make all the numbers work out exactly right, I went ahead and showed more significant figures, so there was no round off issues here. I also am relying on us remembering all the stuff we did before. I mean, it's shown here, but this triangular load here that starts at 0 and goes to 150 pounds per foot over this 9-foot height. I've already calculated that resultant force of 450 pounds, which is 1/2 base times height of the triangular area. And we know that the resultant is acting at 2/3 of the distance from the pointy end, or 6 feet up. So all this is stuff that we have done before, just as a reminder. We have a couple of options here, right? Because I said you can keep the left or you can keep the right. So let's keep the left the first time. This is not really the option I would choose, but let's go through it so you can see, compare and contrast the differences. I wouldn't choose this side because it's just got a lot more going on. But let's do it. So I drew my free body. So I've got my cut just a smidge to the right of D. My shear, since it's on the right-hand side of the cut, is pointing down. My moment is counterclockwise. The normal force always points away. And good, I've got everything I need. So let's go ahead and start solving. So solving forces in the X is going to find my normal force for me, right? So I have 450 pounds minus 352.17 plus NDR. Always put your internal unknown force in your equation so that when you solve for it, you get the correct sign. And I get that it is actually minus 97.8 pounds of compression. So that is the internal axial force at D. To find the shear, I'm going to sum forces in the Y. So I've got minus 354.84 minus 200 minus VDR equals 0. So my shear is going to be minus 555 pounds. So it really is pointing up. No bother. We leave it pointing down since that's the way we drew it, and we say that it's negative. No big deal. And now to find the moment, I'm going to do counterclockwise positive moment about point D. I like to do moment about the point that I'm cutting. Especially when we get into shear moment diagrams later on in this lecture, sometimes the shear can be a function and not a number. And so summing somewhere else is really problematic. Summing at the cut is just good practice. You don't have to. You can sum anywhere else. It would always work. You would still get the right value. But let's just sum at D. So I've got moments at D, counterclockwise positive. So MDR is positive, plus 450 times 3 feet. And that's because that's a counterclockwise moment. So that's positive. And then I've got 352.17 times 9 feet, and that's a clockwise moment, so that's negative. And then I've got 354.84 times 2 feet, and that is positive because that's going to be counterclockwise. And so I solve, and I get that the moment at D, just to the right of point D, is 1,110 foot-pounds. Let's do the exact same example again now, but do the other free body, the free body on the other side. So I'm going to keep just this little nub over here to C. I've got the applied FCD here, which is from that 2-force member from the previous example. It's got a force in it of 563.4 pounds acting at 80 degrees from the horizontal. Note that I now have my shear pointing up, my moment clockwise. My axial force is always pointing away. Note that the 200-pound force is acting here at D is not shown because I'm cutting just to the right of it. Maybe it's just an angstrom. I don't care. It's to the right. So the 200-pound force is not on this free body diagram. You keep the parts you're keeping. You get rid of the parts that you're getting rid of. And at the cut surface, you draw all of the internal forces that are there and solve for them. So let's do that. Sum of forces in the x equal to 0. Guess what? Exactly the same value. Sum of forces in the y. I've got 563.4 times the sine of 80 degrees plus VDR gives me minus 555 pounds. Notice when we flip the signs, everything stays exactly the same. Then I do sum of moments. Again, I'm going to do it about point D. I've got minus MDR because now it's pointing as a clockwise moment in its assumed positive sense. So it goes into my statics equilibrium equation as a negative. And then I have plus 563.4 pounds times the sine of 80 because only the vertical component is going to be causing moment about D. And that's going to be times a distance of 2 feet. And I get that MDR is, again, 1,110 foot-pounds. So you can see it doesn't matter which side you keep. You'll always get the right answers. Some ways are easier than others.